we started discussing performance. And we said performance and quantitatively assessing performance of computing machines is a very important topic currently in computer architecture, to be able to scientifically and using a data-driven methodology determine whether a machine is better than another one or not, right? Because there are so many factors, and in reality, it's even way more complex than we're going to discuss in this lecture. Because what if we have multi-cores, multi-threads, heterogeneous computing? So the equations that we're going to cover in 4DM4 is in fact the first level equations, right? It's like the first order, but there are multiple consequences into it that we're not going to discuss. At the end of the lecture, I will mention some other resources if someone is interested further. We discuss this further in the graduate course. I will share also, I guess, a very nice book about how we measure performance in modern computer architecture, but this goes beyond an undergraduate course, right? So it's just, this is for your further reading if someone is interested. What we're going to cover in the lecture is the very basic information, right? How to do some data-driven analysis given two machines, you have an application, what makes sense, what not, is frequency is the only factor that you should use, or there might be other factors. Good. So our starting point yesterday was this distinguish between latency and throughput. And we said both can be good metrics for performance measurement. In terms of latency, the lower the latency, the better it is. In terms of throughput, the higher the throughput, the better it is. And we said both are not, in fact, the inverse of each other, or they are not reciprocal. In many cases, there are trade-offs between both. If you can improve latency, this will come at the expense of throughput. And we give the pipelining as an example that we'll see later on. Or if you improve throughput, this might come at the expense of, well, in fact, if you improve throughput through pipelining, for example, this comes at the expense of latency. If you want to improve latency, throughput will become less. And this is very common in real-time embedded systems, as we mentioned yesterday. Those that are like in the self-driving car or like a nuclear plant or something of that sort. Good. And then we said originally, at the very beginning, when people started quantifying how do we measure performance for computing, this is early 80s, they said, okay, we can use millions of instructions per second as a metric. And some research papers and even some white papers from industry, many from IBM, as we said yesterday, appeared using that term. And it remained there for a couple of years. Well, million instructions per second. So if a machine has a higher MEPS than another machine, that means it's a better machine, right? But then as we discussed yesterday, this is not, in fact, a very valid metric. And the reason for this is, well, first of all, ISAs are different than each other. And we had the discussion about CISC versus RISC, x86 versus MEPS, for example, or ARM, where one instruction from Intel can be translated into tens, few, like 10 or 20, in worst case, for a RISC instruction set. So it's not an apple-to-apple comparison. But also within the same ISA, not every instruction is doing the same amount of work, right? So even in a MIPS instruction, we said the add might take 1 cycle, but doing a floating point division might take 20 cycles. Doing a load store operation from the memory that is a miss might take 100 cycles, right? So even within the same ISA, different instructions do a different amount of work. So they are not equivalent. And for that reason, only using MEPS as a metric is not really very representative. So what to do? So we want to come up with an equation that defines for a certain program running on a certain IC or a certain hardware, what is really the performance of that application. And if you observe what I'm saying right now, I kind of made two limitations, two restrictions, right? We said we are measuring the performance of an application running on a machine, right? When I say for an application, that means for a certain number of instructions. So the application now is defined, good? And running on a particular machine, that means I fixed the ISA, right? And also I fixed the frequency that the machine is running at. And doing this takes us to what we call the iron rule of performance, or iron rule of computer architecture, which is the total execution time of an application. Just a very simple equation, in fact. If you think about it, I want to measure how much time this application takes. Okay, this application has X number of instructions. So I say the number of instructions per program. And then every type of instruction takes different number of cycles. So I say the number of cycles for this instruction. And then for the frequency of the operation, this is in terms of cycles, right? So I didn't bring in the time factor yet. So I multiply by the clock speed, which is seconds per cycle, just to get the total equation in seconds. Good. So if you only take the first two terms, this gives you the total execution in cycles, right? Because if you think about it, instructions will go by instructions. They will end up cycles per program, right? For example, you say one application is taking 1 million cycles. Good. But 1 million cycles, still there is a vague information here. How much is a cycle, right? Because one machine might be running faster than another machine. So here comes the last term, which is the frequency of the machine. So you say, okay, how many seconds do I have per cycle? And this will, the cycle will go by the cycle. This gives you a number of seconds per program, right? So the final output is an absolute time, seconds. Good? Makes sense? So let's take them term by term and try to see what impacts each term. Like for the first one, when we say instructions per program, is this like a hardware information or a software information? Does this depend really on, or both, but mainly one? Like, yeah.
Probably mostly software. Decide how many instructions are.
Great. And you said mostly because you think there is some hardware tail into it?
A little bit, in that the software is dependent on the infrastructure you're running it on, so you might have different instructions depending on what system you're running it on.
True. Great. So thanks, Arjun. So basically the idea is it's mostly software because the number of instructions, as we said yesterday, in fact, there is a many to one, you remember this many to one mapping between the high level C and the multiple instructions, right? So we had this in the first lecture, and we said if you write a C program and then you run it through the compiler, you can end up with multiple assembly representations to the same program, right? But at the end, if you take one of them, then now you fix the number of instructions, right? So for a particular assembly code of a program, you have a fixed number of instructions. This number of instructions, yes, depend on the compiler, which is also software, but mainly depend on the application itself. If you are doing a swap operation, it will be completely different than doing a CNN code, right? So the number of lines of code or number of instructions will depend heavily on what the application is doing. But then we said it's mostly dependent on the software, because think about it. We said even for the same application, like take swap as an example that we also mentioned yesterday. If you are running an x86, we said there's a swap instruction in Intel, which means in fact your program can be translated mostly to one instruction, right? But then if you are running on MIPS, you will have multiple number of instructions because, well, there is no such complex instruction that encompasses everything. So in that case, there is still dependency on what ISA you are running at to determine the number of instructions of an application, right? Great, but it's mostly software. So this is the first term, instruction per program. What about cycles per instruction? What do you think? I have a table somewhere later, but what about cycles per instruction? Yeah. Mainly hardware, that's true.
It depends on the computer architecture, on like how long the task will take, like how long an addition will take.
Exactly. This is almost purely hardware, right? Every instruction will take a number of cycles based on how well optimized is your hardware. Is it pipeline, not pipeline? Do you have, for example, a floating point? Very early machines didn't really have floating point native in their actual processor pipeline. They had it as a coprocessor, right? And they were added later in beginning of 90s. Do you have instructions that support this type of operation, or you need to float it to a coprocessor? So it's mainly hardware. And what about the last term, frequency? Hardware, right? Like this is like your laptop is running at 3 gigs, but my laptop is running at 2. Then it's something dependent heavily on hardware. Good. We will do this comparison a lot while you are going for performance and also designing the hardware. Is what depends really mainly on hardware, what depends on compiler, what depends on software. Because at the end, you need to make a decision whether in fact changing, for example, your hardware or upgrading it or taking that feature makes sense or not. Because if you try to upgrade the hardware for something, to optimize something that does not even depend on the hardware, well, that's not a wise decision, right? Good. Now, CPI, or cycles per instruction, this is a very common term in computer architecture. It's called CPI, number of cycles per instruction. First of all, is CPI a latency or a throughput? From our discussion yesterday, cycles per instruction, is that a throughput metric or a latency metric? Latency, right? And the reason is we say cycles per instruction, so I fixed the load, the effort that I'm doing, which is the instruction that I'm executing, and measuring how much time it takes, cycles, right? So it's a latency metric. Now, 1 over that metric is, there is something called IDC, instructions per cycle, which is a throughput metric, right? For a certain number of cycles, or for a period of time, which is cycles, how many instructions I execute. Good. And again, once we look into pipelining, we will realize that IDC is not really all the time 1 over the CPI. Now, to give you some example about cycles per instruction, we say program A executes, well, integer, floating point, and memory operations. And now, because we execute different types of operations, then they take different number of cycles, right? So integer will take 1 cycle in this machine, memory will take 2, and floating point will take 3, right? Now, I only have 1 equation for execution time. How can I plug? So if I go back to this equation here, I only have cycles per instruction here, right? So there is a single term, but now I have different number for CPI based on the number of operations. So which one do I write? Right? If you have an application that have floating point operations, integer operations, memory store, load and store operations, branching or control logic operations, and everyone is taking different amount of cycle, which one do I use to really plug into my equation? Cycles per instruction. Well, yeah, the average. And the reason for this is you don't care really about the single execution of 1 instruction. You care about the total execution of the program, right? So you take the average there. So what you will do is you would say, as written here, I will calculate the CPI of the program based on the average overall for that program. Now, this average will depend really on how many instructions are there in my program that are integer, right? Because if my program, for example, is 90% integer, then most of the time I will be spending 1 cycle. Right? But if, on the other hand, my program is mainly memory, like a memory copy operation, for example, in that case, most of the time, all my instructions are taking 2. So there is one missing piece of information here that doesn't tell me how much percentage is there for every instruction type in my program, right? And I'm saying, well, it's not really missing, because if we really did, I intentionally skipped it at the beginning. Say program A executes equal, right? So equal here, the assumption in this program is there is an equal percentage between the 3 types. So it's like 1/3 are integer, 1/3 are floating point, and 1/3 are memory, right? So if I want to do the math, I would say 1/3 of my program is integer, so it's 1 over 3 will take 1 cycle, 1 over 3 will take 2 cycles, 1 over 3 will take 3 cycles, and then simply everything will sum up to 1, right? And then I will end up with an average of 2, right? Which means, well, on average, an instruction in my program will take 2 cycles, right? Another way to convince yourself that this is a good representation is to ignore about this average discussion and say, well, if I say 1/3 and 1/3 and 1/3, assume my program have, well, 1,000 is not divided by 3. So let's say it has 333 instructions, total number of instructions, right? Because remember our equation, the first term is number of instructions, right? So I have a total of 333 instructions. And I'm telling you that 1/3 of it is integer, 1/3 is floating point, 1/3 is memory. So that means I have 111 integer, 111 floating point, and 111 memory, right? So I want to calculate the total number of cycles taken by the program. What do? I will multiply 111 by 1, and then by 2, and then by 3, right? That's what I will do. Take every single instruction in my program, determine how much time does it take, add all of them up, right? Let's say what I have done here. Make sense? And then I need to multiply by the frequency, but I'm only calculating CPI here, so I don't care about the frequency term. So this will give you simply the 3 and 2 is 5, and this is basically 6. So you'll end up with 666 cycles. right? Makes sense? But the point here is the reason we're calculating the average is usually when people look into CBI, which is a middle term, they don't have information about the first term, which is total number of instructions per program. So I don't have that number, right? I only give you percentage. I only said it's 1/3, but 1/3 out of what? In this example, it's 1/3 out of 666, right? And if I want to take that average for the 666 cycles, what I will do is I will divide, well, this is the total, and then I will divide by the total number of instructions. So it will be 666 over 333. What is the value I end up with? 2, which is the same one I calculated here, right? Because took the total divided by the total number of cycles divided by the total number of instructions, right? So if you have the total number of instructions, simply you can do the math, add everything up, and then you are done. But CBI as a term, people usually use when they don't have the total number of instructions of the program. And in reality, most of the time, you might not have this, right? And it might not really matter much, the total number of instructions. What really matters is the percentage, the ratio of the type of operations you are doing, right? And if you end up with 1 million instruction versus 2 million instruction in a program, okay, the execution time will increase by 2, but as far as you're doing your CBI correctly, you're good, right? So out of the total equation, total number of instructions, going back to the total equation here, multiply by CBI, multiply by the clock frequency. Usually, people simplify this equation by only looking into that term. Good? And this is why I didn't give you any info about this total number of instructions. I only give you the average of things, like 1/3, 1/3, 1/3. And I also didn't mention the frequency of the processor A. If you go back to this problem here, this one, we didn't talk at all about the frequency, right? Or the clock period of the hardware. And I didn't talk about the total number of instructions. So the only thing you can calculate is in fact the CBI, or the average CBI, given the ratios. Questions? Yeah.
Instructions per program, is that like static for a certain ISA? Or?
You mean the ratios, like?
Yeah, like how do you know instructions per program? You have to calculate that as well, or is that like based on what?
Yeah, for example, the 1/3, the integer, the 1/3. Or you mean the first term? Those are not. Yeah, the first term in fact depends on the program, right? So you have to have a program in assembly fashion because compilers can generate different assemblies, and then in this case you can do the total count. So this is something that you need to calculate or get that info to be able to get the total execution time. But usually people abstract that, like if I want only to focus on CBI, which is the average term, right? To be independent of number of instructions in the program, I ignore that term, right? Yeah. So to say like out of these 3 terms, people usually put more emphasis on the middle one. Yeah.
Imagine when you're programming in high that have to step down to a lower level and that has to be made into machine code. It would be pretty difficult to determine what of your software that you've written is actually like translates to a memory operation or a swap or whatever. Is there a tool that does that? Or?
Excellent question. And this is the topic of Lab 1. I would assume you missed yesterday's lecture. Did you?
No. You
were in the lecture? Okay, great. So basically, so if you remember, we had this big lecture of the bin tool and like what do we do in the lab. So bin tool is a binary instrumentation tool that part of what it does, it can give you ratios of, well, I have X integer, X memory, and then it's floating point and branch control and this thing. And even architecture simulator. So what we do in Lab 1 is we will do this from the bin tool, but we will run the actual program through the simulator, and we'll get the stats out of the simulator and try to correlate this to the bin tool. Right? So we'll do it both by running it in as if it's hardware, which is our model, and then by doing the binary instrumentation. Right? So there are tools that try to, usually this is in computing system research or in computing system industry, it's called program profiling or binary instrumentation, right? How do you analyze your programs to obtain these statistics to be able to do some meaningful operation about them? And this is a very important topic for a reason. Is your very first, remember when we said the story of how to come up with a new machine yesterday in an industry, this architect that will sit down and have the coffee, right? What is your starting point? Your starting point is a pain point in the current architecture. But your current architecture is targeting certain type of applications. For example, if I'm targeting applications that are mostly floating point, scientific operations, for example, I cannot really say I'm going to spend all my next 2 years optimizing our hardware for integer operations. It doesn't make any sense, right? You can have the best integer operation in the wallet, but it's not going to gain you any market in the field that you are targeting, right? So you need to know exactly out of the applications you are starting, you're trying to serve, what are the ratios of the instructions, because this will give you the bottleneck of the hardware that you need to optimize, right? And we will have a type of problems that tells you for this type of application, if you make a choice between a branch predictor, something that, for example, try to improve control logic like if statements and loops, versus having a better cache, which is going to improve the memory type of operations, which one do you pick? And in fact, the answer will depend on your program. If I have mostly cache memory operations, then I should really optimize. There's a very common rule that will come later on in performance in computer architecture that is saying make the common case fast, right? So the final goal of performance, of average case, of throughput is to say, look into your common case of your program and make it faster, right? If you only have 1% of your program as memory, get the best memory in the wallet, but you're going to only get 1% gain out of the total thing, right? So you have to focus on the common case. And this is why profiling applications is very important. Good?
So the binary tool would give you that breakdown of the
Yeah.
embedded tool.
Yeah,
Gives you the breakdown.
Yes, exactly, yeah. Any other question? Okay. Great. So another example, but this example is a little bit more, yeah, this is what I was talking about, in fact. It came earlier than what I thought, but this we'll also do in the lab, in lab 1 and lab 2. So assume I give you an application that has 50% integer operations, and I'm telling you that they take 1 cycle. They have a 20% load operations, memory load operations take 5 cycles. The store only takes 1 cycle, it's 10%. And then the branches again are if control logic function calls, 20%, and they take 2 cycles. And now your decision as an architect is to determine, should you really decide to add a branch predictor? We'll know more about this later on. But what you need to know right now is that it reduces the branch cost from 2 cycles to 1 cycle. So it optimizes really the branches by 50%. And then you can add a cache to reduce the load from 5 cycles to 3 cycles. So the new machine, you have 2 options now. If you pick up option A, your numbers will be exactly the same for everything, except that for the branch, it will go from 2 to 1. For machine B, you will leave the integer as is. The load will go from 5 to 3, store will remain 1, and this will remain 2. Now your decision or the solution to this problem is to determine, should I pick option A or option B? How to proceed about this? Maybe I give you 10 seconds. Yeah, please go ahead. Yeah, but what do I calculate then? Sure. But how? It's again using the CBI, right? So the CBI that we calculated in the previous slide, let's say I will take the CBI of the baseline. Baseline means before your modification, right? So if you calculate the CBI for the baseline, what you will do is to say, well, I have 50% of instructions will take 1 cycle, 20% will take 5, 10% will take 1, and 20% will take 2, right? This gives you 0.5. This is what? 1.5. This is 0.1, and this is 0.4. So you end up with 0.5, 0.5. This gives you 2. So you have a CBI of 2 for the baseline, right? Now, CBI for option A. What did I really improve? For option A, you have chosen the branch predictor, right? Which will take this one from 2 to 1. So the only change you will have, everything here would remain the same. This one will go from 0.4 to 0.2 because you have 0.2 multiplied by 1, right? So you save a 0.2. So CBI of A will be in fact 1.8, right? You can do the math yourself. CBI for B, what did I save? Is for the load, which is this one. It goes from 5 to 3. So 0.2 multiplied by 3 is 0.6. 1 compared to 0.6, it means that I save 0.4. So I go from 2 to 1.6. Which one do I choose? Option B simply, right? So it's the problem seems fancy. It's in fact an interesting problem, but the math is very simple, right? Questions? Good. Okay, so here is some discussion about what we were talking about. Microarchitects often ignore dynamic instruction count, right? Why that's the case? Well, we want to ignore, it's not that we want, it's usually we ignore the dynamic instruction count for two reasons. First of all, it's mainly depending on the application. And yes, you are optimizing your hardware for a particular application, but for a particular application family, not for one application, right? So the ratios of type of instructions in a program is in fact consistent across families of operations. So what I mean is you have categories of applications that are, for example, scientific computing, right? And for scientific computing operations, they're mostly floating point because you don't want to go to the bank and simply realize that you're losing dollars or you're gain, maybe you want to gain dollars, or you are losing dollars out of your balance because there was a truncation somewhere in the floating point, right? So most of the scientific and financial calculations are heavily floating point based, right? What I'm saying right now is not for one application. I'm talking about a family of applications, right? Usually we call these benchmark suites, right? So you simply have a family of applications that are mostly floating point dominant, right? The information I have for this family of applications, not the number of instructions, because a number of instructions will differ from an application to another in that family or in that suite. But the information I have is, for example, there are 70% floating point. So I get the ratios, right? And for that reason, when you architect a system or develop a new hardware for this type of applications, you are not doing it based on a certain instruction count for one application. You're doing it based on the instruction type ratios for a family of applications. Okay? So that's the reason why usually computer architects ignore the total instruction count. Another reason, as we said yesterday, it really depends on compiler optimizations, right? So for the same application, maybe you are able to reduce the number of instruction count by 50% if you do a good job at the compiler, right? So the actual instruction count doesn't really matter much for the hardware. Okay. And now if we ignore the instruction count, I lost the first term. So that what remains in my calculation of the operation, it remains CBI by the clock speed, right? Good. Now, going from that, so we started from, well, the actual absolute math of the execution time of the application, which is number of instructions, CBI, clock speed. We said computer architects usually ignore number of instructions. Maybe compiler engineers would like this, but we usually ignore this. So we go to that second equation. Now, if you think about someone going to buy a new machine, a laptop, I don't know if some of you are old enough for that, but like 10, 12, 13 years ago, I used to have a hobby of assembling my desktop myself, right? So you would go to a mall or somewhere and then buy the like you buy the processor chip separately, the Intel chip, you buy your RAM separately, you buy the motherboard separately, and everything, and then you assemble them, right? So in that case, if you're doing this, or maybe even now when you buy like a whole machine already pre-assembled to you, a normal one would look into this equation to determine whether, when I say a normal, like a layman, that is not an engineer, not you, before that lecture, right? If you go to buy that machine, are you going to say, okay, well, I calculate the CPI, I calculate the clock speed, and then I determine that this machine is better than this one? Or what do you usually do? Well, mostly what I have seen is that, in fact, people are ignoring this term completely and looking into the clock speed, right? Saying, running at a higher speed. Maybe now, not as much, you look into number of cores, memories, mainly, but this is only for a reason. And the reason for that, does someone know why we are no longer looking much into the clock speed and looking into these other terms? Yeah. The clock speed doesn't matter. Yeah, we have saturated, exactly, thank you. So somewhere in, they will say different years, but you can say 2008, 2010, every 2 years, Intel used to have, for example, a new chip that is doubling the frequency, right? 1 gig, 2 gig, 2.4, 3, 3.5, right? But then you reach the limit, something that we call the power wall or the frequency wall. where you are no longer able to increase the frequency. And it didn't really become that important that much because, okay, everyone has almost more or less the same frequency. And we moved to what we call the multi-core era, where, well, number of cores matter and the memory matters more, right? Yeah. Moore's law is one reason, but it has been done, in fact, before Moore's law, right? So there is a very interesting article that I can also share with everyone on Avenue, that this hitting the frequency wall is not really, it has some factor, but it's not in fact because of Moore's law. Moore's law, up until the moment, is still really functional to some extent, but we lost that frequency thing almost 15 years ago, right? So it came before it, and it came before it because of mainly the power. You are no longer able to really cool down your chip in an easy way, right? If you look about servers, for example, they use like cooling material nitrogen and things that are not very, you wouldn't like to have tubes in your laptop, right? So that means for this particular use case, the frequency is stabilizing. We're no longer able to get something from there. Let's move to another place. We're going sometime later on to have a very detailed lecture. Well, it's not very detailed in terms of detail, but I call it the bird's eye view. We go through the different revolutions of computer architecture, starting from very simple sequential processor, and then we discuss why people did leaps into multi-core, for example. And frequency was one big reason for that. Okay, so usually if we ignore all the other new factors of multi-core and memories and having GPUs and that stuff, and SSDs, like we're talking mainly about the processor architecture, clock speed was in fact the thing that people focus on the most, right? But what we try to argue for in this lecture is that clock speed, it is important, but you cannot really ignore CPI, right? And here we're having an example that we can say, assume processor A has a CPI of 2, but it has a clock speed of 5 gigahertz. And then a processor B that has CPI of 1 and clock speed of 3 gigahertz, assuming the same IC and compiler and everything. Which one do you choose? Well, if you give this to someone that doesn't know computer architecture as much, you say, well, 5 gigahertz, that's almost double the frequency, I'll just go for it, right? But in reality, if you do the math, you might really realize that B can be faster, right? Given that it has half of the CPI. Right? Because if you do the equation, you multiply 2 by 5, gives you 10, but then you multiply 1 by 3, it gives you 3. Well, it's in fact not 2 by 5. It's 1 over 5 and 1 over 3, because it's in fact the clock period. So you get 2 over 5 and you get 1 over 3. Which one is better? 1 over 3? Yeah, I will trust you. I have to, or go to my son and ask him for that math. Yeah, but if 1 over 3 is better, this is basically a proof that simply B is better than A, even if it's in fact almost half of the frequency, right? Now let's take this a little bit practical. What would make, is that really a practical example? Well, the real answer is yes, because you might end up with a machine that is 5 gigahertz, but let's, for example, I'm telling you it has 4 cores only, right? But then machine B might have 8 cores, right? Or it might be hyper-threaded, that every core has a couple of threads, hardware threads, right? So there are means, even modern means, to improve the overall performance for lower frequency machines, right? And then you have to look for the collective metric. This is why it's important to look for 2 terms together, not only the frequency metric, right? Good. Questions? Okay. So now, another discussion point of the equation we had, where CPI is part of the factor, when we say what does latency or throughput of a certain chip really mean, remember we said we constrain our discussion to a particular application or a set of applications and hardware. So it might not really mean much that you talk only about the hardware. Similarly, it might not mean much to talk only about the software, right? So what we are saying here is that latency of a chip or throughput of a chip, in fact, doesn't mean much until you associate it to a particular workload. What is a workload? Workload is basically the application we're talking about. right? So I'm targeting scientific applications. Do I have a good understanding of how these ones operate, what type of instructions they execute the most, and how to optimize them? And because applications differ a lot, everyone right now can do their own program in their laptop, right? You need some representation. Like as someone working as an architect in a company, it doesn't make sense to you say, I have 1 million type of applications that everyone somewhere in the world coming up with a new application I need to put and try to optimize for, right? So you need to narrow down your focus into some representative applications for the market you are trying to target. Good. And we call these usually benchmarks, right? So benchmarks are representative workloads from a certain domain. Like, for example, there are benchmarks for scientific computing. There are benchmarks for AI workloads. There are benchmarks for cloud computing, benchmarks for embedded systems, for automotive. So if you think about any market, benchmarks, in fact, for usual, what we call general purpose computing, like the desktop market and the laptop market, right? And in fact, the most famous one used in computer architecture right now, it's called, or the most general one, there is a one called SPEC, which is this one. Big benchmark suite, and this is their website. Usually these benchmarks, who comes up with them? Well, engineers from industry, different companies, researchers, they have some sort of consortium, they keep discussing, they write programs, they discuss them, and they end up with some representative workloads, right? So it's something not a single one is doing, but in fact, an organization that simply maintains these benchmarks. And SPEC, for example, is a benchmark suite for CPU, like for normal laptop workloads, right? I/O, web development, mail. For example, one of the benchmarks in SPEC, in fact, is GCC. So they have a benchmark for the GCC compiler. Is it the actual GCC compiler? No, it's a representation of it. Something that's trying to mimic the same percentages of instructions that GCC would go through. Good. Okay, so this is what is a benchmark. There are different types of benchmarks, and all of them are used in, again, industry and in academia. There are what we call toy benchmarks. These are very little programs, very short. They are usually not very representative to a real application, but they serve a certain rule. This rule, for example, can be, I need to have a very first check whether what I'm doing is running or not. Like your Hello Wallet for the hardware, right? You might be surprised, but in reality, the very first test you do, for example, when a chip comes back from the fab, is you want to just bring it up by Hello Wallet, right? Well, is that a workload? Well, it's just a toy example, but it serves a purpose at a certain stage. You cannot really stop and say, I'm done with verification. Just your very first step. Good? So toy benchmarks are used in this regard. And then there are what we call kernel benchmarks. These kernel ones are not very large benchmarks, so they are not really the actual application, but they are focusing on the functions that are most representative in a particular application. For example, if GCC is handling, I don't know, parentheses and like brackets and the ordering of operations in a certain function that does some, let's say, a stacking operation, right? So in 2SI, you had stack data structures, right? So you write a kernel that simply mimics the same operation using a stack data structure. You call this a kernel, right? That is does for example, program ordering operation in GCC. Something similar to FFT, for example. You had FFT in communication, I think, right? So you have an FFT kernel that represents FFT operation in automotive domain, in signal processing, etc. And then we have synthetic benchmarks. These ones are handcrafted, and these ones are very commonly used in verification. And they are synthetic. What does it mean to be synthetic? Someone sits down, an engineer or an architect, and try to write a program that is targeting a particular feature in the hardware, right? For example, if I'm trying to test how does my memory operate on a random operation, I will write a pointer chasing application. You know what is a pointer chasing application? USI, like you keep jumping pointers across the memory, right? So you don't. So in an array type of operation, you go sequentially in your memory, right? Because there is a contiguous segment in your memory, element 0, element 1, element 2, element 3. But in a pointer chasing fashion, you keep jumping, for example, by adding and removing from a linked list or a tree or a graph, right? So in that case, the operation is truly random, which is going to stress the memory. So if your memory is optimized for random operations, which is Many of the solutions right now are trying to do that because of the graph data structures and the CNN architectures. Then you'll write a synthetic application that does a pointer chase, which is very simple to write, right? With your 2SI knowledge, you probably can write. Even in fact, by the end of 2SH, I think we had an exercise for linked lists that tried to do that. Another application is streaming, for example, right? Streaming is going to resemble something in like data processing. Like I'm doing something like a video processing or an internet speed test or something of that sort. You have a lot of streaming operations, which means you block a big chunk in your memory, like in terms of megabytes or sometimes gigabytes, and you go sequentially across it, right? And this, we call it a streaming benchmark. And this is also a synthetic benchmark. Good. And then there are the real programs, which is the very complex ones that does not only the kernel operation, but the true representation of the actual benchmark. And I give you the example of spec with GCC inside it as a representation of, well, that's a real program that represents the GCC operations. Okay. So why I'm discussing all of this, because it's very important to understand, to be able to assess the performance of your machine, you need to run it across certain type of applications, right? So you need two things, application or a workload and your hardware model. And in lab 1 and lab 2, this is exactly what we're going to do, is you will be given certain type of applications. You will be running them through BinTool to get their instructions and model. You will run this through the simulator, and you will really get the breakdown of load operations, memory operations, etc., and how much performance you get. Good? Questions? Okay, I think this is too much. Let's have a break for 7 minutes, and we can start 1:30. Okay, so to continue the discussion about the benchmarks. So over the years, researchers and engineers came up with different benchmarks. Well, for example, maybe I can continue with this thing because it's quite interesting. You see some names here. GCC I already mentioned. BERT, UniBERT, scripting language. They do model, in fact, as a benchmark, right? Maybe this is coming from, well, it's very old computing. But there's also PCF2, which is the compression algorithm, right? If you compress files in your laptop. So most of these applications target a normal day-to-day user general purpose computer, right? And then they also have another floating point version where they focus mainly on floating point operations. And this is written in C++. It's very complex. We did a lot of research, but we are not going to see in the lab. Where did they go? We're not going to see it in the lab because it takes a lot of time to run spec. Just to give you a sense, it takes us a week to run some of these experiments in a classroom, right, of computing. So it's a lot of time. I don't want you to wait in front of your machine for a week to get some numbers, right? So we're not going to use these. Right? We're going to mainly depend on toy plus synthetically generated benchmarks. But in addition to spec, over the years, also people develop more targeted or different flavor benchmark suites for other reasons. Like for example, originally spec was single-threaded. It was like 10, 20, not 10, but maybe 25 years ago, there wasn't truly multi-threaded hardware, right? And this is one point we'll touch on later, is that multi-threading can be done in software and hardware. We're talking about hardware multi-threading here, where your actual core is in fact multi-threaded. So there wasn't such thing. So in that case, most of the workloads were single-threaded. But once we started having parallelism and multi-core and multi-threaded workload, multi-threaded machines, you needed workloads to be able to test those and see how really the multi-threaded applications communicate with each other, right? So there are other multi-threaded applications like Splash 2, something like coherence that we might see later on in caches. You will only see for multi-threaded workloads, because if you have every core in your machine running a single application that is not related to another one, it will reside, and you know this from your operating system course, it will reside in a separate process, like a certain place in the memory that is not communicating with other processes, right, for security reasons. But if this is a multi-threaded or a parallel workload, you have to communicate with each other. So the cores will start communicating, right? And this will cause issues with consistency, coherency, some advanced architecture topics. So you need to cover some of this. So people came up with multi-threaded workloads that you can run in multiple cores. One of the very common techniques, something that's called OpenMP, which is a library that is used for parallel workloads. Those, for example, in CS, we have a course called parallel computing. In reality, we also have a graduate course in ECE for parallel computing, but I don't think you take any parallel computing course in your undergrad, right? This is an elective by Professor Kazim that is offered first time this year, I believe, right? That might be talking about that. Good. So another point, so we talked about workloads and why we ignore the total number of instructions. We focus on the average CPI, and then the clock speed is something related to the hardware. Now going back to the average CPI story. When we say average, which average? Are we talking about the mean, geometric mean, harmonic mean? And does it really matter? And in reality, it matters a lot, right? It's that this topic and which mean to use is beyond really the undergrad. I don't want to confuse you. But just to let you know, there are research papers published in top venues that people accuse each other that you are using the wrong time of mean, which means your results doesn't mean anything, right? Because simply just used it wrong and you made a conclusion that doesn't make sense, right? And this is why I believe this slide here says, okay, one of the things that architects often get it wrong. But a general rule of thumb, and again, the actual details are beyond this thing. The book that I was mentioning to you at the beginning have a very detailed discussion about what type of mean you use and why, and this kind of things. But we usually use arithmetic mean for types, latencies. If we talk about number of cycles, like if you have multiple applications, for example, 5 applications, you have the total execution time for each application. If you want to say, on average, these applications, I take X cycles, then you just average over absolute numbers or scalar numbers. Well, just normal mean is enough. But if you want to average over rates, something like a throughput, for example, or over a speed up, like comparing a machine to another machine, so the normal mean will not really work, right? Because you cannot really have an average of ratio using the normal mean. So you either use the harmonic mean or the geometric mean. Okay? And again, I wouldn't really try to stress much to this point because there are a lot of details that we don't care about. But there is another important point here, that how do we calculate speed up? And this comes from the rule of thumb that I mentioned to you, that is very common in computer architecture, especially general purpose computing, which is make the common case fast, right? So I took my application, I analyzed it, I got the average number of instructions. I want to make a decision. I will make a decision to maximize the performance or improve the performance of the common case, right? And common case means the number of, like for example, the type of instructions that appear the most in my application, right? And this is called Amdahl's law. It's a common law in computer architecture that tells you if you already speed it up. So let's have some visual discussion first. Just make sure I don't confuse you. Assume that this is your total application, total number of instructions in your application. And let's say there is a certain type, so I'm going to color them based on types. There is type 1, type 2, and let's say type 3. I will do it like that. So what is the most common case? It's type 3. So this is type 1, type 2, type 3. In this case, let's say type 3 is the half, right? So this is type 3, right? So my decision will be based on this rule of thumb, make the common case fast. I will try to accelerate type 3 of instructions, right? Now, assume type 3 was running, let's say it was taking, every instruction was taking 10 cycles, and I managed to reduce it down to 5. So I made 100% improvement on the latency of that application. Like it's like a 100% speed up on this type of instructions, right? From 10 to 5. Now, does it mean that your application total execution time has been reduced by half? For sure, no, right? Because this is just left the same. I reduced this one by half. In reality, how much did your total application reduce now? Can we calculate that from what I just told you? I told you that 50% of your application is this type. This just remains the same. I wouldn't even give you the ratios, it doesn't matter. I managed to reduce this from 10 to 5, which is basically, well, it's you call it 100% reduction, 50% reduction. It depends on whether you call about ratios or slowdown. Doesn't really matter. But at the end, you made that 2x improvement. Okay, you reduced by 50%. What is the improvement of the overall application execution time? Can I know it? Yeah. Half of that. Yeah, because this type of instructions is half, and you improve that half by half. So in fact, it's 1/4, right? If I want to visualize this, I would say the new application, these two types remain exactly the same, but this one will only take half of the time. Now, if this takes 100, which means this one takes 50, this also one takes 50, then this one reduced from 50 to 25, so the total it takes 75. So I improved it by 1/4, right? How did I calculate this? Intuitively, right? From the visualization. Can we have this in a closed form math? Yes, that's exactly what Amdahl's law is doing, right? Amdahl's law is saying, if you want to calculate the total execution time, the new one, after the speed up for the common case, you split up your application into two fractions. If, the one you accelerated, and 1 minus f, which is the one that remains the same. The one that remains the same didn't improve at all, so you don't divide it by anything. But the one that is accelerated, you divide it by the speed up, right? So in our case, I had f in fact as 0.5, right? Because it was half of my application originally. So 0.5 remains the same, and the second 0.5 improved by 2. So I got a total of 0.75, right? That's exactly what we did, but we did it visually, right? So this is Amdahl's law on how to calculate the new execution time of your application. If you want to speed up, you basically divide the new by the old. So this is the speed up. Or the old by the new, because the old is larger, right? So it gives you a larger than one fraction. Questions? It's a simple math, but you have to have the intuition behind it. Why that's the case, right? F is the only one that is accelerated. It's only a portion of the application that is accelerated. This is why we divide it by the speed up. 1 minus f is the factor that I didn't touch. It will just remain the same, right? And in that case, it just remains as is. Yeah. Amdahl's law. I will just write this here. I'm not sure if that's the actual. Yeah, Amdahl's. Yeah, this is. Sorry, it is. Good. Any other question? Okay, so you can do a lot of math here. Like if you say if is in fact 95% of your application. So I managed to accelerate 95% of my application by a 10%. So it's the speed up is 1.1. How do you get the math? You simply say, well, 1 minus 95 remain the same. Here you only have a 10% improvement, so you get this thing which is also close to 10%, as you can tell, right? So the higher the fraction of the application you improve, the better the overall execution time comes up, right? So there are two factors here. Like going back to our figure, how large is the portion that you accelerate? The larger, the better the total execution time, right? Because you improve a larger portion. And how fast you improve it. The larger the improvement, the better it is overall. Good. So it's F and S. These are the two factors that really impacts how much total execution time improvement you make. And if you think about it, take the limits. If F is 0, what do I get? Yeah. No change. That's the old application. I didn't do anything, right? Okay, if the speed up is just as is, so it equals 1. I didn't do anything for F. What I end up with? No change. If the speed up is infinite, what do I get? So what does it mean to be even speed up of infinite? You took a fraction and you improved it to the level that it does not even appear at all. Just Oracle, right? Yeah. Yeah, this will be removed completely because it will be 0, but you are still left with 1 minus F, right? Yeah, Arjun.
Yeah, so your fraction F basically is something.
Yeah, exactly. So if we look into this figure, this one here, completely removed, but I'm still left with the second half, right? So, and this is a comment that we'll make later on, right? Even if you're able to speed up your fraction by like a big deal, you still are left with the slope, right? So we will extend that iron, this rule of thumb of make the common case pass later on, right? But let's continue with this. If F is 1, what do we get? It's just, what does it mean to be F equal 1? Yeah, exactly. I speed up the whole thing because it's simply F is my total application. So I took the whole application and speed it up. So it will be simply, this will be removed and it will be 1 over S. If you think about it, TU will be Q all over S, right? That's exactly if you speed up the whole application with a factor of S. Good. Yeah. Whoever was asking about the name, that's really the name. Yeah. So here there is a comment that we're talking about our infinite S, right? Favor and make the common case fast. But you have to remember that at the end of the day, the more you try to squeeze performance out of F, you become more limited by the 1 minus F, right? So eventually be limited by that slope on. So make the common case fast, but eventually you will be limited by the case that you didn't accelerate. Good. Okay, some other takeaways. I guess we already mentioned all of them. Latency and throughput that you use for performance depending on really what you care about. Single instruction latency doesn't matter. As a single instruction, what you care about is actual task execution, right? Our actual program execution. So if you can really accelerate the overall application through throughput by pipelining multi-core, this is what really matters, even at the expense of increasing the instruction latency. Most of the techniques that we're going to study in this course, in fact, will address the trade-off between latency and throughput by favoring throughput over latency. So we'll improve the single instruction latency while we improve the overall throughput by other factors like pipelining, out-of-order execution, caching, and memory, etc. Good. Okay, great. One possible way to improve, for example, the throughput of an application is to do pipeline. And we're going to spend a lot of time about pipeline, so you don't have to worry too much about the actual details here. But the idea is very, very simple. This is something that you usually do in your daily life anyway. So let's have a very basic example. Assume you go to the library, and then what? You want to study computer architecture from books, right? So there are like 10 books in computer architecture. You go to the shelf. Well, this is focusing on computer architecture. There are 10 books that you want to look at, talk about performance. And then you have a table that is somehow, let's say, a few meters away from that shelf. One technique to say, I go bring one book, go and sit down, start reading the performance chapter from that book. Once I'm done, close it, go back to the shelf, bring the other one, do the same thing, right? Another technique is to say, well, I will go there 10 times. Why should I do this? I just bring the whole 10 books, sit down in the table, open one at a time, and then go back and put them back, right? So what you do here is you try to get more instructions to maximize the output of a certain operation you are doing, right? In reality, this is not only by pipelining, but it's also, in fact, something called superscalar later on. You go and fetch more memory. Remember, yesterday we talked about fetching instructions from the memory. You don't fetch one book, but you fetch multiple books, right? So there are techniques that we perform to optimize our efforts in a daily life that also people use in computers to optimize the effort. Pipelining is saying, if you have different functional units, the functional units we were talking about yesterday, arithmetic operations, floating point operations, memory, register file reading, and at one point at a time, one instruction is using only one function unit. Like, for example, the add might be using the ALU. All the other function units are idle. I'm not using them. Well, can I use them to optimize my performance? The answer is yes. Bring more instructions. Usually, or hopefully, they would have to access different types. And you can pipeline them by sending them to different function units. And you create what we call, and this is also very common in factories, for example. If you look into a video about Tesla factory, how to optimize the production line, you will find that every single place in the production line have their own function. And they operate in a pipeline fashion, right? I do one job at the moment while another one is doing another job. Then once they are done, I'm done with my job, pass it forward, and then it comes to me, right? Right? And in that case, you are pipelining the operations. Everyone is doing a particular operation. But at the end of the day, if you are at the end of the line, like the production line, you will see the whole car assembled faster than if one was taking that car from the very beginning until it's fully assembled, and then go and take another one, right? So pipeline is very common in daily life. What does it improve? Well, it improves the overall throughput. If you think about the actual one car in the production line, it's just taking the same time or even more. Because if someone was only doing the whole car, I mean, if expert enough, then it will do it faster than you do a part and then hand over to someone else, right? This handing over would create a context switch problem, right? In computer architecture terminology that we'll see later. But if someone is doing it fully, then simply it works very well, right? For a single car. But do you care about a single car and you're done? In a factory, that's not what you care about. What you care about is how fast you can get that car out, the throughput itself, right? So if you look into a single car, the latency is higher. But if you look into the overall performance, throughput is in fact better, right? Exactly in pipelining here, we impact latency because we keep hopping an instruction from a register to another register, from a function unit to another function unit. But the throughput is higher by looking into how many instructions they execute in a cycle, the IPC, it improves. Good. Same thing if you're working in a team in a project. If you say, well, I'm the expert, I do everything on my own, well, it might be true if the project is reasonably sized for a single person, right? But most of the time, if it's a complex enough project, it will be good if you find an harmony and then how to divide the work well and then simply pipeline your operations. Good. Great. So now, more useful CPI breakdown memory. Yeah, so going back to the overall equation that I would like to write here, number of instructions, or the instruction count, and then CPI, and then clock speed or clock period. So assume now we are in lab 1 and lab 2 and we want to measure CPI. Oh, they do. Interesting. The application crashed for some reason. Okay, so going back to the total equation we have the instruction count, we have CPI, we have the clock period. So how do I measure the CPI or even the total execution of a program in a real machine, right? For example, during the break, we were discussing with a colleague of you what happens post-silicon when you have the hardware back and you run the actual machine for verification. You want to do some measurements, right? So there's something called performance counters on the real hardware that gives you some numbers that you want to correlate to your original. Again, going back to the architect story, someone promised that you might be improving CPI by 50%. Now we have the machine back, right? This is the day where the architect will be absent from work, right? Because simply, it will never become true what you promised earlier, right? So what would happen is you want to correlate this to the original performance numbers from RTL to the original performance numbers from the real the cycle accurate high level modeling. How do I measure this in real hardware or even in your current laptop? Is there a way to know if I run an application, how much time does it take? What do you think? Yeah. Thank you. So this is usually a typical way of doing it in your program, or maybe even outside of your program in a terminal or something. Take a timestamp before, take a timestamp after, and then subtract. Good. It's a used method. What are the drawbacks of that method? Yeah. Accuracy. And why accuracy is impacted?
It might not be the shoe stop at times.
Yeah. Yeah, true. That's one reason.
So accurate.
Exactly. That's also another reason. A third reason is that you're not running this application alone. At the very least, the operating system is already running, right? Yeah. Yeah. One reason is simply not remember. So first of all, well, the last one I said is that there might be other things running, and then what did you say? Yeah, but why? What was it?
The first one was computers aren't 100% accurate with time. So
Yeah, but I guess you said another reason.
And then I said if you measure before and after, it might not be the truth.
Yes, true. That's in fact the main reason why doing it, for example, in terminal or outside of the application. This is not the true time where the application restarted, because you stamp the time, you launch the application, but in between there are, in reality, in terms of the clock frequency of the CPU, there might be hundreds of cycles, right? Maybe even thousands of cycles before and after. So impact accuracy. Sometimes people kind of circumvent this by putting the timers inside the application itself, like before a function, after a function, right? Which is a little bit more accurate. This is very common in embedded systems, right? Because you have crystal clocks as well in your MCU, right? But it's still also not very accurate because, well, the actual CPU cycles are on their own, they are not 100% accurate, right? In terms of measuring time, you still be context switch to go to the timer function, do the math, and then bring in the number, right? Is there another way of doing this that gives you more accuracy? In reality, most common, like most what we call COTS, like commercial off-the-shelf machines, the ones that are in laptop and embedded systems and desktops, they provide what we call performance monitoring counters, right? There is a real hardware dedicated to take performance numbers out of the hardware, and they expose this to registers. In reality, those that are commonly using Linux, there is a tool, software tool, that exposes this counter to users. It's called BERF. I'm not sure if you heard about it. Has anyone heard about BERF before? Good, great. So you can really read these counters, and the difference between these counters and the timer is that these are counters inside the actual hardware that monitors, for example, memory requests, instruction fetches, and increase the counting accordingly. So it's very tightly coupled to the actual execution pipeline. Good. And well, there is BERF in Linux, but there is also a tool from Intel for Windows that I forgot what it's called. Volgrand, I believe, or something. That's so I forgot the actual tooling name. But there are many tools that try to expose these registers to the software level, right? And performance monitoring counters are, in fact, the main tool used for this sort of post-silicon validation. Almost every silicon company, in addition to the performance monitoring counters exposed to customers, they have what they call built-in self-test hardware that is not exposed to customer. It basically can be exposed in a test setup through sending some particular bits to the actual chip, and they do more testing, also tightly coupled to the actual execution, right? It's called built-in self. I don't know. Did you hear that term before? Again, yes. Anyone that had an internship in a verification team might have heard. Yeah. Oh, you heard about it. Okay, thank you. Thanks. So going back to the main question, how do we really measure CPI and execution time? Well, if you are pre-silicon, doing modeling is simple. You are either doing it in C++ level, high level, as we do in the lab. So we have access to everything. It's white box. We also have stat counters, mimicking performance monitoring counters in Maxim, for example, for CPUs. If you're doing this in RTL, you have the chip scope and probes in your actual either Xilinx or COTS, and you can add registers and look into the RTL code to count stuff, right? But if you are both silicon, where it's just a manufactured chip, then you have these performance counters that you can use. And this is true for CPI and also the total execution time. And in fact, it can also give you a breakdown of the CPI. So something you would do in lab 1 is you will be asked to look into the total number of instruction types for the application and what is the average execution time of this type. And based on this, you calculate the total CPI of the application itself. Okay, so we said at the beginning that architects usually ignore the total dynamic instruction count and focus mainly on CPI. And in reality, most of the techniques are in fact targeting improving either CPI or IPC. Some of the techniques are in caching, pipelining, out-of-order execution, speculation, which is like branch prediction, for example, superscalar processors, multi-core, multi-threading. All of these target is in fact to improve the CPI or the IPC, good? The middle term of the total execution time. Well, can Moore's law help with the CPI? Well, generally the answer yes. You give me more capabilities. If you give me more transistors, I can have more processors. I can have higher performance processors. I can add more registers. I can add more arithmetic logic units, more parallelism. So it can generally help. Well, simply the most common technique right now is the multi-core, but this is a discussion that I would defer to this bird's eye view lecture that we'll do later on. To summarize, Amdahl's law is saying total speed up, you make the common case fast, but at the end you would be limited by the non-accelerated base. If you optimize the 50% of your program, even if you magically make it disappear, you only did a 2x speed up because the other 50% still remains the same. This is the S equal infinite and F equal 0.5 in our equation. What generally should I do? You optimize 1%, don't over-engineer capabilities, not be designed for actual average and not big performance. Yeah, so it's again, this is a discussion that again I will defer for later because we have a more detailed discussion about it. What is it saying? What we said earlier is you try to make the common case fast. So for example, don't say I'm going to optimize 1% of my application and then I leave the 99% the same. This is not a good trade-off, right? And most of the cases, in fact, some improvements in one part will impact the other parts. That's why Amdahl's law also is, in fact, a good closed form math, but in reality, it might not always be true. Like Amdahl's law is assuming F and 1 minus F is completely distinct, right? I improved F by S, 1 minus F remains the same, right? Well, that's true if you're talking about a branch predictor and a cache, something that's completely separate. But if you talk about adding a pipelining stage or another ALU, where you create more contention on the memory bus, then in reality, they are related. So most of the time, maybe I should write the equation to make sure you are with me. So I have 1 minus F plus F over S. Most of the time, improving F by S might in fact impact badly, in a bad way, the other part, 1 minus F. So it doesn't really remain the same. It might be multiplied by a factor S dash to make it worse, right? But we will ignore that part for now. Okay, summary is, when I want to measure the total execution time of an application, it's the dynamic instruction count multiplied by CPI multiplied by the clock speed. The number of instructions per program is dynamic. It depends really on the program, in the compiler optimization and the ISA. And we traditionally ignore in architecture. Compiler engineers care more about it. We focus more in CPI, which is cycles per instruction. It's still function of the program. How it's function of the program? The ratios, right, of the instructions in the program. It's in compiler because what does it generate in terms of assembly, the ISA, and the microarchitecture? Clock speed is mainly a function of the hardware, as we have already said. If we want to optimize, we focus mostly on CPI, and we create multiple techniques to optimize it. Yeah, and well, improving clock speed, pipelining, and some other techniques can also help with it. Are we good? So I was intending to start in the actual control path. Well, no, in the actual ISA review, but I don't think it will be good to start on this in 10 minutes and then, well, we still have 15 minutes. So I think. So what do you think? Should we start the ISA review and let me open the slides and see how it looks. Okay.
How do you think we're going to answer?
Yeah. Well, I guess I asked the question, then I was afraid I would answer. So I said, okay. I would assume I didn't hear it. Let me see. No, I don't think it's a good idea. Okay.